Another formal test that you can use when you want to detect heteroscedasticity, check for the presence of heteroscedasticity, is called Goldfelt-Quandt test. Let's consider the following, our usual two-variable model, where y is a function of x. So according to the test procedure, first of all, what we need to do is we need to order or rank the observations according to the values of the independent variable, beginning with the lowest x value. So we rearrange our data set in such a way that we start with the lowest values of x and we go all the way down to the highest value of x. After we've done this, we need to omit some number of central observations from the data set, where C is specified a priori, and we take the remaining observations and we split them into two equal groups. Goldfelt and Quant suggest the following procedure for choosing the value of central observation. So they say that C should be around 8 when the sample size is 30, and C can be 16 when the sample size is about 60. So let's say we have 30 observations. Therefore, we will need to delete 8 central observations from our data set, and after we've deleted those central observations, we take the remaining observations and we split them into two equal groups. After we've done this, we need to estimate two OLS regressions using the first half of the observations and using the other half of observations. And from these estimations, we need to obtain the respective residual sums of squares. Please be aware that the residual sum of squares in each regression has the following number of degrees of freedom: n minus c, so n minus the number of central observations, minus 2k, where k is the number of parameters divided over 2. So this is the number of degrees of freedom. And in the last step, we need to compute the ratio, the f-test, where we take the residual sum of squares from the second regression and divide it by the degrees of freedom from this regression. And here we have the equation for the degrees of freedom. And we divide everything by the residual sum of squares from the first half of the observation divided by its number of degrees of freedom. And the decision rule is the following. So if the estimated F statistic is greater than the critical F statistic, which we take from the F distribution table, then we reject the hypothesis of homoscedasticity. So we say that our residuals are heteroscedastic. However, if the estimated F statistic is lower than the critical one, than the one from the table, then we accept the hypothesis of homoscedasticity. So we say that our residuals are homoscedastic. In case there is more than one x variable in the model, like for example this equation where we have 3 independent variables, then we can rank order the data according to one of these x's. And if a priori we're not sure which x variable is appropriate for rank ordering, then we can conduct the test on each of the x variables, or we can choose the x variable using the Park test. So what is meant by conducting the test on each of the x variables is the following. So it's just we will undertake the same procedure step by step, but for each x variable. And if you don't want to do that, you can also, and you would like to practice Park test, then please be my guest. Here is the Park test that we discussed with you, right? So here we can apply this test to see whether this beta coefficient is statistically significant with each of the x's. And if it happens that beta is statistically significant with one of the x's, then you can conclude that data is heteroscedastic, that your residuals are heteroscedastic. However, this test has its own limitations. For example, the success of this testing procedure very much depends on the value of C, so on the value of the observations, central observation that needs to be removed. So if it happens that you choose this number incorrectly, then your testing might be a failure. Also, the success of this testing procedure very much depends on identifying the correct x variable with which to order the observations. And again, even though I've told you how to choose the x variable, the appropriate x variable with respect to which we can order the data, it might still happen that you make somewhere a mistake, or for example the park test produces invalid results because of heteroscedasticity present in its own equation, and then your whole estimation procedure is actually incorrect. Therefore, please be aware of these limitations when you are choosing the appropriate test for heteroscedasticity.